Hi everyone, welcome to Math Spellbook. I'm your host Peter, and thank you all for joining us today. In addition, I would also like to thank the people that gave a follow, while the stream was not streaming. So big thanks to Slade Darth, who gave a follow. And for all you guys that basically followed the subscribe to the YouTube channel, thank you for being subscribers on the YouTube channel. And if it's your first time here, welcome to Math Spellbook. So we've been doing a lot of progress, basically learning about the origin of the numbers. So I shall join my lecturer Sascha, and hopefully he will enlighten us today on basically more about the rationals, and hopefully we'll get into sequences today. So let me just join up with him on Discord. Hey Sascha, we're on stream.
Hey Peter.
Okay, the floor's all yours.
Alright, so I will recall what we did last time. So last time we were done with the construction of the integers, and we started the construction of the rational. And I sort of guide you through how we define addition and multiplication, and I sort of left. I leave you to check that you get a field. And today we're gonna start to talk a little bit about some analysis concept stuff.
Okay.
So today we're gonna try to talk about absolute value and sequences.
Okay.
So last time, we defined Q as the Cartesian product of z times z. When the second factor you want to remove a zero, quotient out by some relationship. And our relationship was like the obvious one. It was basically the cross multiplication test. So we said that this fraction is equivalent to this fraction if we add AD times BC. So we get those two guys are equal. So when I multiply the diagonal together, I get the same result. Okay.
Okay.
And last time, Peter basically guided us. I didn't redo much. He basically told us the definition of addition and multiplication. And all we did.
No. I'm the simpleton in this in this one. Hey, we just had a math pun, simpleton.
So today we would like to do analysis, and for that we need to talk about ordering first.
Okay.
So maybe I would just talk a little bit in general about ordering. So again, it's a very general thing, so we can define for any set. So if X is a set, an ordering relation. Well, actually, I'm gonna use So if X is a set, and we have R a relation on the Cartesian product of R with itself.
Mm-hmm.
So you just, I mean, a relation is basically just a subset of X times X.
Okay.
So nothing here scary for now. It's just a bunch of pairs.
Okay.
But we want to have like some good property to like recover what we intuitively think of what ordering is. Okay.
All right.
So
And
it's
R
called.
is just and R is just a regular set, right? It's not the real numbers, right?
Yeah, R is just a subset of X times X. So
Okay.
I wrote R because it's a relation. So R, big R relation. You know. It's called a partial order.
Mm-hmm.
If we have the following.
Mm-hmm.
So here I will just make sure I don't mess up because
Yeah.
I don't want to be in trouble. Partial orders. Okay, so first of all we have reflectivity.
Mm-hmm.
And I mean, as I said before, so usually when you have a relation, usually instead of writing x, y's inside of the pair, of R, instead of our relation, usually we don't really use this notation. We usually use something like that.
You're right. Yeah.
Yeah, but here I'm gonna use. I mean, here as we're talking about ordering, I will use a very intuitive notion. I will just instead of writing R, I will write it with less or equal to. Okay.
Mm-hmm.
So what's the first property? So for all x inside of big X, we want x to be less than or equal to itself.
Okay.
So this is reflectivity. This is pretty much the same property we had for equality.
Mm-hmm.
The second one will be for all x and y inside of big X. If we have that x is less than y and y is less than x, then x is equal to y. Okay.
Mm-hmm.
And the last one will be transitivity. So if now I get if I get three guys, so I get x, y, z inside of x, and I have x is lower than y, and we have y which is less than z. We want x to be less than z. Okay.
So basically, the third one is like they're all x and y and z is an element of x. X is supposed to be less than or equal to y, and y is supposed to be less than or equal to z. Thus, okay, I see now.
So here I will just give you some example. So this is called a partial order, and you will see where the partial come from.
Okay.
In English, we usually call it, usually people call it partial order, but sometimes you will see people call it poset.
Poset? Okay.
That's another way that people use to describe those.
Okay.
Call them. So example. So the obvious one will be the integers with the usual inequality. So you remember we defined those a few lecture backs, but x is lower than y if there exists some z inside of n, such that y is equal to x plus z, right?
Okay.
So this is like kind of that's usually the one we think about, the first one. But there is also other partial order that are quite simple. Example 2. I forgot I'm writing in English, so you have to put the A to example. Example is kind of a funny word because in French most of the time we put like some A I mean, sometimes there's like words in French and English which are very similar, but usually they're kind of off in the spelling. Like in French, we usually spell it with the A. But example is one of those exceptions where it's backward for some reason.
Oh, interesting.
Yeah. So let S be a set. Okay. Any set.
Okay.
Then we can have a very simple partial order on not exactly on S, but on something else, on the power set. And the equivalence relationship, not the equivalence relationship, sorry, the partial order on this set will be the inclusion.
Okay.
Okay, so maybe I can just give you an example. So let's maybe take S to be something concrete. Let's take, for example, S to be the set that contains 0 and 1. Okay?
Okay.
Just because I don't want the power set to be too big, but I think this will be big enough. So the power set of S is the set of all subset, right?
Yeah.
So it contains the empty set, it contains all the singleton, and it contains S itself, which is the set 0, 1. Okay? And the partial order we have on the power set is the inclusion. So just if you forget.
So
the
is that
definition
symbol the same symbol as a subset, or is it the same symbol?
Yeah. This is the same. Subset and inclusion are
Okay.
mean the same thing.
Okay.
So just to be sure.
thought I was like, oh wait, there's a curve there, so it's not less than or equal to.
So you have S1 and S2 inside of the power set, so that just means they're a subset of S. You said that S1 is a subset of S2. If for all X inside of S1, you also have that X is inside of S2. And I mean, it's kind of easy to check. It's a partial order because okay. So first axiom said that you have to check that an element is less than or equal to itself, right? Obviously, any subset is contained is a subset of itself, right? So any subset verify this. Okay, here I just want to warm you a little bit. So here I put a little dash below the curve less than or equal. Less than, I should say. Sometimes people don't put it. And usually, I mean, if you take it like very strictly, it would mean like this is a proper subset, which means like you cannot have equality. Okay. But often in the literature, what you will find is that people are somewhat lazy and you just don't put the little dash below, but they mean they don't mean a proper subset. Usually in the literature, usually people use this symbol and this symbol like to mean the same thing.
So the one without the line and the one with the line, they kind of treat them like interchangeably to mean the same thing. Yeah. So you have to be a little bit careful. Is the one without, because like the one with the line, right? Like that's when all the elements in one subset is in the set that it's supposed to be a subset of. Like, I mean, when we think about it differently, because I think I've seen that in the Book of Proof, where it's like when they don't have the line underneath, it's sort of considered as it's a subset, but all the elements in the subset are not in the set that it's supposed to be a subset of.
Yeah. So it's a proper subset.
Okay.
So this guy is supposed to mean that, but usually people like get kind of sloppy and use the two as the same meaning. So what usually people wrote instead is they write something like that.
Okay.
To mean like it's a proper subset. It's not equal to the whole thing.
Oh, so basically the one without the line and the one with the line and the cross, that's basically the same thing?
Yeah.
Okay.
It's a bit confusing, but
No, it's fine.
I guess we get.
If anyone wants to correct us or like inform me more about it, just put it in the comments down below if you're watching this on YouTube, or if you're watching this on Twitch, put it in the chat.
So for any subset, if we have that S1 is contained inside of S2, and we have that S2 is contained inside of S1, well, this implies that S1 is equal to S2, right? That's kind of a strategy to prove equality between set, is to show that we have the 2 is inclusion, right? We have I mean, usually this part we sometimes call it the double inclusion. Okay. And third property, it is a transitivity, which is a bit obvious here. So if I have I don't know, S1, S2, and S3, which are subset of S. If I have that S1 is a subset of S2 and S2 is a subset of S3, again, from the definition of subset, it's pretty clear that S1 will also be a subset of S3, right?
Okay.
Okay, so here there is like some kind of feature in the second example which make it a little bit different from the first example. So when you're talking about integers, you can always compare 2 integers, right? You can take, like, for example, 3, you can take 5, and you can, I mean, ask the question which one is bigger, right? For the second example, that's not always the case. Not all elements of PS are comparable. For example, if I give you the 2 following subsets, I give you the subset that contains 0 and I give you the subset that contains 1. Well, you cannot really tell which one is contained inside of the other, right? Like, it doesn't make sense. Neither A is contained inside of B, nor B is contained inside of A. So those are not comparable, which is a difference between what we had with the integers.
So when you mean by comparable, that means like, does that mean that they don't have like the same elements, or like, is there something we can't, I guess, like, show that they're the same, that they have the same elements? Like, what is that supposed to mean, like, comparable?
So what I mean by comparable is our so if we use our partial order that we have on the, for example, for the second example, we have the subset inclusion relation, right?
Yeah.
It does not always make sense to try to compare 2 subsets.
Okay.
For example, A and B here, there is no like way to say that A is contained inside of B or B is contained inside of A.
Oh, so basically you're just not sure which is the subset and which is the actual set that the subset is holding. Okay.
Yeah, you cannot make sense which if B is bigger than B. There's like no. I mean, with our order, we give the definition of order we gave. There is no way of telling which one is bigger. So those are not comparable.
And this is when, let's say, A or B is not a proper subset. This is basically like if one has like all the elements of the other, but we just don't know which one is the main set and which one is the subset, right?
I'm not sure I'm following the...
So my question is that, does this only follow for, say, let's say if A is the subset, but we did not know that, right? And it contains all and B contains all the elements of A, right?
Yeah.
My question is that when we are talking about making the sets not being comparable, right? Are we talking about like that scenario? What I described is like all the elements in A is contained in B, but we just don't know whether B is the subset or A is the subset? Or...
No, so in the example you described, so you said that B contains all the elements outside of A?
Yeah, but we just didn't know that.
Well, I mean, okay, so I mean, it's kind of not a very something that can happen, right? Because if you know that B has all the elements of A, you know that A is contained inside of B.
Yeah, it's just that like I don't know if we're dealing with like both with proper subsets and subsets that we know that the elements of that subset is within the set that we're comparing it to, or is it only for like say proper subsets, or is it for?
No, it works for any subset of S right there.
Okay, that's what I was asking.
Yeah. So here the problem is neither. I mean, if you take an element, so what's the element of A? There is only 0, but 0 is not inside of B. Therefore, A is not contained inside of B. But the other way around also doesn't work, because if you take what is the element of B, there is only 1, but 1 is not inside of A. Therefore, B is not a subset of A.
Okay.
So you don't. So sometimes they are not comparable in that regard.
Okay.
So those are so. I mean, as the name might suggest, on the top of the definition, as for the definition of a partial order, we use the word partial, right?
Mm-hmm.
In some sense, it's like they're. It's not like a full ordering. Like there might be stuff that we cannot compare.
I think we got a question in chat by Aspire. Hello, Aspire. First time chatting. Welcome. What's the best part of your day so far, my friend? Is the set of all the sets that does not contain itself has itself as a member? Oh, I think that goes back to Russell's paradox, right?
Yeah, I mean, we've shown there is no set in Zermelo-Frankel. There is no set that verified this.
We can never escape Russell's paradox.
Yeah, we checked that axiom of regularity does not allow that. So yeah, we did that. We did that like
curse
the first
you, Russell's paradox.
Yeah. Okay. So I mean, the second example is kind of a weird one, right? Because usually you will expect stuff to be comparable, right?
Mm-hmm.
But that's not the case in that here.
Okay.
So what you can do is you can enforce the ordering to be a little bit stronger. You can talk about total ordering, okay?
Okay. Like, I'm still trying to understand what you mean by make the ordering stronger.
So here the problem is there are like some stuff that are not comparable, right?
Right.
Like if you compare the first example with the second example, in the first example, it always makes sense to ask if some integer is bigger than the other, right?
Right.
Like, I mean, you can always make sense of the definition. In the second case, you cannot always make sense of the, I mean, so there's like example of elements which are not comparable, like the one I just
yeah, 0 and 1, yeah.
So the first one is kind of like a better ordering in some sense. It has more like properties. Right? It's not just like the basic 3 properties we stated before. It has more stuff that make it that give it some property that the second one doesn't have, right?
Okay, so when we're talking about ordering, right?
Yeah.
Like, did we just define what ordering is, or is that
just...
okay, like...
So formally, it's just the definition above.
Okay,
so it's just a...
Could you redirect us to that? Oh yeah,
yeah,
like if X is a set, this portion?
Yeah.
Okay. Oh, and including 1, 2, and 3 within this definition, yeah. Right? Okay.
Yeah.
Okay. Lucky I wrote that down. All right.
And example 1 has like more properties than those 3. There's like others a property that we can.
So
have.
This little thing that's in between X is less than or equal to Y. That's an implied symbol, right? In between that one, yeah.
Oh, this is a if and only if. So the double-sided arrow.
Oh, okay. Because it looked like a bullet, and I was like, "Oh, is that an implied symbol?"
The less X is less or equal to Y is shooting the existential quantifier.
Okay. Okay. I guess we can continue on with the total ordering.
So what is the total ordering? It means that I mean, there's a little bit some loose that you can have in this definition, but the important part we want is a partial order is called totally ordered
you for the follow, E-Raven Violet.
So what's the property you want? So 1. So
Okay.
basically it's like yesterday we talked about ringing fields, right?
Mm-hmm.
And we said a field is basically like a rich dude, right? I mean, at the end of the day, it's a human, but it's just richer, right?
So wait, hold on. A partial order is called the total ordering or total order?
Yeah, total order, yeah.
Okay. Because it looks like it says totally ordered. That's why I asked.
Well, we can say totally order, so it's fine.
Oh, okay.
Yeah, there's like kind of some adjective you can put between the word order and
Mm-hmm.
get some stuff. So what you want is that you want stuff to be comparable. So what we will ask is for any x and y
Uh-huh.
inside of S. Okay.
Mhm. Okay.
Either we have x is less or equal to y, or y is less or equal to x.
Okay.
Okay.
Mm-hmm.
So here the difference between a partial order is that here we're forcing element to be comparable.
All right.
Like to be a total order, you must be able to compare everything.
Okay.
Everything is comparable. So for example, example 1. Is a total order. But example 2 is not.
And which examples are we pointing out?
So the 2 example I wrote before.
Okay. Let me just scroll up, see where your cursor is. Ah, okay.
Those 2 guys. So the first example was the integer with the less or equal symbol that we used to.
Mm-hmm.
And the second example was the subset relation.
Okay.
So the first one is because you can compare every integer with any other integers, and the second one is not because we can find a counterexample like the one I just I gave you.
Mm-hmm.
And you should.
Writing those. Okay.
And I mean, if we go back to what we were doing before, so we were interested about numbers, so integers and real numbers.
Mm-hmm.
For now, I mean, what we expect is the rational and the real number to have a total order, right?
Mm-hmm.
Like we want the 3 properties we want before, but we also want to be able to compare every element with each other's, right?
Mm-hmm.
So what we're now looking for is a total order on Q.
Mm-hmm.
And define a total order on Q. The set of rational. Okay, so here I'm gonna give you the definition, but I will leave the check of checking the total order as an exercise. Okay.
Okay.
Because it's kind of like not. I mean, it's not very. I mean, if you struggle with it, I can help you, but I think it's better if you try it for yourselves.
Yeah, like every other math proof exercise.
Yeah, because it will help you like to like I was about to say inhale the definition, but I don't think that's the right word to use in English.
No, I think I think like basically be enveloped enveloped in the definition.
Yeah.
So I would ask like more of the technical details within it.
Yeah. So you can play a little bit with it and then maybe understand it a little bit better.
Yeah.
So what will be the definition of partial order? So, okay, first of all, I want to start with a remark.
Mm-hmm.
So, a fraction looks something like that, right?
Right.
And I mean, obviously there's like a quotient and stuff like that.
Mm-hmm.
But given any fraction, it's always possible to assume that b is positive. Okay.
Okay, why is that?
Well, okay, let's maybe give an example. So let's take an example. So let's say we have the fraction 1 over minus 2. Okay.
Okay.
What I will show is this fraction is equivalent to the fraction minus 1 over 2.
All right.
Okay.
Okay.
And I mean, if I want to check if two fractions are equivalent, I just need to do the simple cross multiplication test, right?
Right.
So what we get when we do the cross multiplication, we get 1 times 2 on the red part, and on the green part, I get
-2 times
Negative
-1.
yeah.
And last stream we actually proved that 2 negatives equal a positive.
Yeah. So this will give you
Two on both sides. Yeah.
Yeah.
Which is equivalent.
Yeah, that means they're equivalents, and basically that's like the whole idea. So you can always assume that your fraction have a positive number at the denominator, because you can always multiply by -1 on the denominator and -1 on the numerator to reduce that case. So now that I show you how we can do it in general, so let's A and B and C and D be fraction. And I assume that B and D are both greater than 0. So I mean, here I use the less or equal I use the inequality symbol, but those are over Z, right? Which are completely fine because we defined it last time.
Yeah, because it's supposed to be a fraction in this case, so B and D cannot equal 0.
Yeah. So what we'll ask is that we're gonna say that those two guys are AB is less than CD if we have that AD is less than BC.
Okay.
So we're sort of doing the against the diagonal. I mean, it's basically the same idea. So you get that.
Okay.
And here you have some stuff to do as usual. So I mean, I recall that fractions are defined up to equivalence, right? So you have to make sure that this definition does not depend on the choice of the specific the specific value of A and B we chose. So I will leave this as an exercise, but exo show this is well defined. And give you a total order. Okay. Are you still here, Peter?
Yeah.
Okay. Yeah. And also this, I mean, also you can prove as an exercise, but I mean, you sort of have to prove like a lot of properties, so you don't have to prove all of them if you don't want. Like, I mean, just prove the one you think.
Did we went over how to show something that's well defined?
Yeah. So what you want to, so I did it a few times, but what you want to do is you want to show that if, for example, EB is equivalent to A primes B primes, and CD is equivalent to C prime D prime, and you also have the hypothesis that B prime are positive and D primes are positive, as I requested in my definition. You want to check that if AB is less than CD, you want to check that you also have that A prime B prime is less than C prime D prime. Okay. So it makes sure it's a well-defined concept of fraction. We don't want, like, I don't know, I mean, I will write something which doesn't make sense, but we don't want like a 1/2 to be less than 1 and a 1/4 somehow, 2/4, I'm sorry, not being less than 1. That would be a problem.
Right.
Because 1/2, b2/4, I mean, as far as fraction goes, they're the same, right?
Mm-hmm.
Because of our equivalence relation. So this is like, I mean, the check I did a few times. I did a few times when we were talking about the integers, like when we wanted to add integers, we had to show that actually when we do this addition, we have to make sure it does not depend on the choice of pair we chose, right?
Mm-hmm.
So it's always the same thing we have to do when we're talking about stuff like that. Okay. Also, here's some extra properties also this thing has. So if A, B, C, D are rational numbers, you have the usual stuff. So if you have A is less than B, okay, then you have that A plus C is less than B plus C.
All right.
So I mean, those are basically like, I mean, you've probably played with inequality once at least in your life, right? And you probably encountered those, right? And I mean, okay, there's like stuff like that. There are also like, if you have A times B, okay, so let's say you have A is less than B, and let's say that C is strictly positive, then you have AC is bigger than BC, right? And if you get that C is negative, then you get that this inequality is flipped, right? You get that BC is bigger than AC in that case.
So it's like A is less than B, and B is and C is less than. Is that D or 0?
That's a 0.
Okay. Just want to make sure.
It's negative, yeah. You usually Q with an order like that would be called an order ring, but we will not really use that
terminology right here.
Yeah, we will not use that, but it's usually when you have an order which play nicely with the ring operation, it's called an order ring, but we don't need that here. Okay. And with that, we're very happy because now we can define absolute value, which is going to play a crucial role to define sequences. I mean, the convergence of sequence. So, absolute value. So let's A be some rational numbers. Okay. So has the inequality symbol is sorry, I did a mistake actually. Okay, I'm sorry, I did a pretty bad mistake here. Okay, so the total order is not the strictly less than equal, it's the less or equal symbol, which is a total ordering.
Oh, okay.
Okay, so maybe I can just write it below. So we say, okay, let A, B be rational numbers. I mean, you probably already know that stuff, but I will just write it as a good measure. So you say that A is less or equal to B if A is smaller than B, or A is equal to B. The reason why you want the less or equal to have so if you just have the strict inequality, just like A is smaller than B, you don't even get a partial order because the first properties fail.
In the list.
Yeah.
Where are the properties?
So the first property said that A should be less or equal to itself, right? So if our relation is strict inequality, then we get into trouble because A will not be smaller than itself, right? Strictly smaller than itself. So it's important here to use the less or equal symbol. Sorry for the typo. Okay, so now we can define the absolute value. So let Q be some Well, actually, we can define it as a function. It's probably better. So we have the following definition. Absolute value. And it's going to be defined as the following, okay?
Mm-hmm.
So what it will do is we'll take some q, some integers, not some integers, some rational, and give you some other rational. And how we're going to define it is we're going to define it as the following. So absolute value of q is going to be the maximum between q and minus q.
Mm-hmm.
Okay.
Mm-hmm.
Are you still here, Peter?
Yeah. Yeah.
Okay. So here I have to just maybe tell a word because why it's well defined. So if we were working over a partial order, maybe it would not make sense to ask which one is bigger between q and minus q.
Mm-hmm.
But as our ordering on q is totally ordered, it means that it makes sense to compare q and minus q.
Okay.
So we can make sense of the maximum here. This is well defined. As q with the less than equal is a total order. Okay. And now maybe I can just give you an examples. I mean those are examples, but so let's say I want to compute the absolute value of 2. Okay.
Mm-hmm.
So the definition just tell me that to choose between which one is bigger between 2 and minus 2, right?
Mm-hmm.
So what will it be in that case?
It would be 2.
Yeah.
Is this another application of the axiom of choice?
No.
No? Okay.
No. Here, the really thing we need to define the absolute value is just the fact that we're able to take maximum of a set with 2 elements.
Is it the maximum of just those 2 only?
Yeah.
Okay.
If I put, for example, minus 2,
Mm-hmm.
well, we haven't changed the set, right? We're still taking the maximum among the same sets, so we get the 2.
Okay.
So what it will do in general, it will make sure that your whatever you give it, the thing you get out will be some positive quantities.
Yeah. Okay. Yeah, the reason why I asked that was because like we have a set and we have 2 numbers, but we know that it has to be at least 1. So that's why I thought that the axiom of choice did play a part in it, but then like you said, it has to be the maximum. So I was like, okay, yeah, that makes more sense.
Yeah, because everything is comparable, we can make sense of a maximum.
Mm-hmm.
Here we'll just okay, and the absolute value is actually the crucial part for getting started into a convergence and sequence. That's really where the magic happens.
Right.
So we're gonna show the following properties of the absolute value. The absolute value verifies the following. Okay, are you ready? Yeah, thank you for
No
that.
problem.
So for any x inside of Q, we have that the absolute value of x is bigger or equal to 0,
Mm-hmm.
and absolute value of x is equal to 0 if and only if
Okay.
x itself is equal to 0. Okay.
Mm-hmm.
The second property said, so wait, hold up.
Mm-hmm.
Okay, so I can use, I will use homogeneity first. So for all x and y inside of Q, we have the absolute value of the product can be written as the product of the absolute value.
Okay.
So this property we usually call it homogeneity. But I never quite figure out why we call it homogeneity.
Maybe someone in the chat can verify if they know.
And the last property, which is important, so absolute value plays somewhat nice with product, but they really don't play nice with sum.
Is this when we get into the triangle inequality?
Yeah, that's exactly that. So the absolute value of x plus y is always bounded by x plus absolute value of x plus absolute value of y. It's called the triangle inequality, as you said.
And this is a big part of real analysis.
Yeah, this is like one tool we're gonna use to get estimate all the time. So what I will do is I will leave the first and second as an exercise, and we will do the third because it's probably the most important.
Yeah.
So we're gonna do it. So we're gonna do the third one. Okay.
Okay. So these properties, right? You can mathematically prove these, right? They're not axioms, right?
No, you can prove them from the definition. Yeah.
Okay.
And you can yeah. We're gonna just prove the third one because it's the important one, and the second one I will leave it as. I mean, those are more like not very important exercise. They're more like routine exercise that you can.
Practice,
I mean, you can do it. Yeah. I mean, they're not really hard necessarily, but.
Okay. All right.
So sometimes you have to pick your battle. So.
Okay.
So all the little check like that, I cannot do all of them because otherwise we're gonna take 2 months to define the real numbers. But
yeah, I get what you mean.
Yeah. Okay, so we're gonna prove the third one.
Mm-hmm.
So what we're gonna do is we're gonna write the definition for the absolute value of x and of x plus y. Okay.
Okay.
So by definition, okay, maybe I will try to be a little bit. So I'm trying to teach you how to write good proof, but I'm being sloppy here, so let me step up a little bit. So let x and y be two rational numbers, okay?
Mm-hmm.
So what we're gonna do is we're gonna be interested on the left side. So what I'm gonna do, I'm just gonna rewrite the definition of the absolute value. Okay, so as we said before, it's the maximum between x plus y and minus x plus y. We can put we can distribute the minus. It doesn't really matter. Okay. And the strategy we're gonna use is we're gonna show that in all the cases, so. I will write it. It's enough to show that x plus y is bigger or equal to absolute value of x plus absolute value y. And that minus x minus y is bigger than absolute value of x plus absolute value of y. Okay?
Okay.
And do you see the reason why?
Let's see. Let's see. X plus y. The absolute value of x plus y is equal to the max of x plus y minus x minus y. Enough to show that x plus y is less than or equal to absolute value of x and absolute value of y. Yeah, I think so. Because like if you break down the absolute value symbols within surrounding x and surrounding y in what you wrote from 1 and 2, you would basically be at the max of like x and negative x and max of y negative y in that case.
Yeah, so the thing I want to show is I want to show that x plus y is less than x, absolute value of x plus absolute value of y, right? But as I did before, I just wrote the definition of the absolute value. I say it's a maximum between those two things, right? So surely if I show that those two things are less than the thing I want to show, obviously the max will also have to be less than the thing I want to show, right? Because at the end of the day, the maximum will be one of those, right?
Right.
So I will have covered all the cases. Okay.
And
so I will show you.
There's like a reverse version where it's like x, the absolute value of x minus y, right?
Yeah, there's there's the inverse. So we're gonna prove the one. So let's prove one. And here I'm gonna use a property that I didn't mention, but it's pretty easy to check.
Okay.
So I'm gonna use the fact that well, let's see, what can I do? So I'm gonna use the fact that x is always less or equal to its absolute value.
Okay.
That shouldn't be like too much of a price. And now what I'm gonna do is I'm gonna add y from both sides. Maybe we can write something like that.
I think you can write it step by step, so the next line it could be like you just add y, or you write then add y at both sides, like you would probably see in a textbook. Yeah, so we have that first, and then like add y to both sides. Yeah.
So like that, right? So this is one of the properties. If I have inequality that holds and I add something, then the equality is still hold, right? And after that, I can do the same for y, right? So maybe I can write it above. So I have y is less or equal to absolute value of y. Okay, maybe I will just write it on the third line because otherwise it's gonna get confused. We can do the same for y. So we again have y is less or equal to y. And now what I will do something a little bit different. Instead of adding x, I will add an absolute value of x. Okay. So I will end up with absolute value of x plus y is less or equal to absolute value of x plus absolute value of y. Okay.
Okay.
But not here I'm done, because maybe I will put some name here, so let's maybe call it 1 and here 2. So if I use 1 and 2 and I use the fact that inequality is transitive, using 1 and 2, we have that x plus y is less or equal to x absolute value of x plus y. So this guy is 1, right? Right, Peter?
Yep.
And the second, if I use the second inequality, I get that absolute value of x plus y is less than the second quantities. And now, now at this point, I can just use the fact that inequality is transitive. Inequality is transitive. Therefore, we have that x plus y is less or equal to absolute value of x plus absolute value of y. So we've shown case 1.
Okay. I'm just like looking it over. Like, let's prove 1. Then we have x is equal to or okay. All right. Okay. I'm just like trying to make sure that the structure of the logic is like solidified in my mind. That's why I'm looking it over again.
Yeah. Is there like part you have question on?
Let's see, because I thought I had a question with the first part where it's like x plus y is less than or equal to the absolute value of x plus y. But when I think about the absolute value logically based on its definition, I'm like, yeah, that makes sense. And my question was kind of answered by my own, I guess, the definition of the absolute value. So
yeah, I mean that's one of the property I left to prove is that if you have an inequality like that,
mm-hmm.
and you add like the same quantity from both sides, then you get you still get an equality.
Mm-hmm.
And that's pretty much what we use here to.
I guess like my only question for this part is that how do you know that say like because you use just x, the absolute value of x plus just regular y is less than or equal to like you know, the absolute value of x plus regular y, and the second one after that is like absolute value of x plus regular y is less than or equal to x, absolute value of x plus the absolute value of y.
Yeah.
How do you know that's the logical structure you need to actually prove that what we were trying to prove, which is x plus y is less than or equal to the absolute value of x plus the absolute value of y?
So basically, so the first, I did like it in two ways. First, I said, okay, I have this guy and I want to end up here, right?
Yeah.
What I can do is I can apply like the property I just tell you that if you had something on both sides, you still get inequality on that guy, right?
Yeah.
But now I'm missing the other
part.
The other part.
Right.
And basically, what I told myself is, what okay, can I like take this part and somehow
transform it into that one?
Yeah. Mm-hmm. And I said, well, what I can do is I can basically do the same thing I did for x, but now I can do it for y. But instead of adding, for example, plus x, which is probably the thing you will have imagined I do, instead add value absolute value of x.
Mm-hmm.
So that on the right side I get the two absolute value like I want.
Yeah, because like in this case, like regular y is sort of considered as a like I guess like quote unquote equivalent to like the absolute value of y, but there's leeway because it's less than or equal to.
Yeah.
So
as I said, so the inequality follow from y is less than its absolute value, and the second one follow from if you add the same quantity from both sides, it doesn't change.
It's logically coherent because you can basically just say like, oh, the absolute value of x, even though we don't know exactly what it is, we can basically say the absolute value of x is there, but then when we say plus y, which we defined as either less than or equal to absolute value of y, which is also equivalent. So the logic structure is still stabilized at that point.
Yeah.
Okay.
And now we're gonna do case 2, which is gonna be very similar.
Okay.
So again, we start with minus. So we know that minus x is less or equal to absolute value of x.
Mm-hmm.
And now we're gonna basically do the same thing. So what we'll get is we're gonna add a minus y from both sides. So we'll end up with something like that. Okay.
Mm-hmm.
So this is again the same property. So if I add or subtract, is really the same thing. There's no difference.
Yeah.
And now I will do again the same trick. So I will do.
So is it like minus y is like less than or equal to the absolute value of y?
Exactly. We can do the same for y. Yeah, you're getting the trick.
I think I've seen it a couple of times. That's why I kind of remember it.
And now what I can do is I can add the absolute value of x from both sides, right? So we'll end up with x plus x minus y.
Because when you're doing the little trick, like say like minus y is less than or equal to absolute value of y, it's still based off the definition of absolute value, right?
Yeah. Because at the end, y the absolute value of y is the maximum between minus y and y, right?
Right.
So as it's a maximum, it must always. I mean, it
Always
must
be
by
bigger.
definition.
It must
Yeah.
always be bigger than negative.
Yeah. And again, we're kind of in the same situation as before.
Right.
We get inequality 1, which is the left side is the guy we want, and the equality 2 have the right side we want, and the other part is the thing. I mean, they're two things equal, so we get them squished in a sandwich. So we get minus x minus y is less or equal to absolute value of x minus y, which is less or equal to x plus y. Oops. But as this thing is transitive, we have that minus x minus y is less or equal to x plus y. Oops. Like that. And this showed the triangle inequality.
And in doing this part, in this case, have we shown the reverse triangle inequality as well?
No, but we can do it quite easily.
Through using the same technique?
Well, actually, usually, usually you can apply the triangle inequality to figure out the reverse triangle inequality.
Mm-hmm.
Maybe I will put it on the sheet for this week with some guidance.
Okay.
I mean, we will not use this thing right away, so
Okay.
wait a little bit. Okay. And now we are very happy because now we have a notion of distance.
Okay.
So now we can talk about distance. So geometrically,
Like before you can carry on, Sascha, Omkar basically said you're pretty good at you teach pretty well. I just felt like you should know that.
Thank you. So geometrically, the absolute value should be think as a distance.
Mm-hmm.
Think as some kind of distance. Okay.
Mm-hmm.
And I mean, here maybe I can give you a little bit more of a landscape view. So if you want to define the distance between two, so let's say let x and y be rational, you will define. You could define the distance as x and y as the absolute value of x minus y. Okay.
Okay.
So this will be called a distance. And I mean, in mathematics, sometimes we call it. We also call them metric, but it should not be confused with metric in the sense of Riemann.
We haven't gone to that level yet. We haven't gone to that.
Yeah, those are not the same, even though they are somewhat related.
Mm-hmm.
At least Riemann metric can give rise to those kind of metric, those kind of distance function, but not the other way around.
Mm-hmm.
And so as it comes out so many times in mathematics, people decided to make it a definition.
Oh, okay.
And it's called a metric space.
Oh,
so maybe I can give you the definition, and I mean, here we're gonna use probably like 2 times this definition because we're gonna build the rational, which is gonna be a metric. I mean, it's gonna be a metric space, and then the real number will also be a metric space. But maybe I can introduce.
Yeah, before you get into that, Aspire basically asked, does all analysis students have to prove these properties before dealing with the reals?
I mean, it kind of depends on some analysis class. For example, my girlfriend took a class in real analysis and she didn't have to build a real number from scratch. They basically lay down a bunch of axioms that they took for granted and did the analysis part. They went a little bit faster into the analysis.
And it's funny because your girlfriend was a film major, right?
Yeah.
She just took math just to take it, like real analysis, so hardcore.
In my first analysis course, we had to build the real number, but
from
basically
scratch.
It basically took a month. I mean, it's pretty much what we're doing right there.
So it takes a month to actually construct the real numbers, to learn it. I mean, to learn how to construct it.
Yeah, basically.
That's much shorter than I thought. But then again, I guess understanding how to do the techniques is probably another story.
Yeah, but I mean, I guess we're kind of doing a little bit more than the number of regular cores you would have in the real analysis course, because we're doing right now.
Yeah, you're incorporating a lot. You're incorporating like a little bit of intro to proof, but then you introduced us to a little bit of abstract algebra, and like I think you're now getting into like a little bit of the real analysis, because now we're talking about distance.
Yeah. So I will give you. So mathematicians found that distances are so useful, they decided to make a concept on its own. So a set. So I will give you the definition, and the reason why I want to give you the definition is because we can state what it means to be a convergence sequence and a Cauchy sequence in the language of metric space.
So what is this definition for? What is this defining?
So we're defining a metric space. So a set M okay, here I'm gonna have to cheat a little bit, but for our definition right now, it's fine to work with Q, but later on we will have to work with
the
R
real
set,
numbers.
Yeah. So M is set with a distance function. So a distance function will be something that takes two elements inside of M and split U. So in the usual definition we will put R there, okay? But for us, it's okay. It's fine for now to use Q instead. So for now, we can use Q. Okay.
Okay.
But usually you want it to be over R. And it has the following properties, which are very similar to the one I just described for the absolute value. First of all, you want the distance. Okay, so for all x and y inside of M, so for any points, you want the distance between x and y to be positive. Okay.
Okay.
And you want equality to hold. So you want the zero. You want the distance between x and y to be equal to 0, if and only if x is equal to y. The second thing we're gonna ask is that the distance between x and y is the same as the distance between y and x.
Okay.
Because otherwise it would be kind of stupid if
they have to be symmetric. They have to be symmetric within distance. So if you're 5 feet away from me, I should be 5 feet away from you.
Yeah. Exactly. Otherwise it will be very weird.
It wouldn't be symmetric and it would look ugly.
Yeah, and what you want next is the triangle inequality. Am I saying right? Oh yeah. For distance you need 3 elements. So you take 3 points. And you want the distance between x and y. The distance between x and z to be less or equal to the distance between x and y between y and z.
So this is a deeper question, but this is something that I think is probably going to be like a higher advanced question. But you could basically tell me like we're not at a level to understand that yet. So, but my question is that does it matter what the the topology of the space with the definition of distance? Like we said in number 2, basically it's like the distance has to be equal to the distance from the other perspective, such as from x to y and then y to x. So I guess my question is that let's say me and you are a distance away, but there's a bunch of hills in front of us. So does basically the distance from me to you basically does the symmetry still hold? So it's basically the same distance away, only like, you know, let's say the space is continuously changing.
Yeah, I mean, for a distance, for a metric space, you want distance to be symmetric. And I don't really know like cases where you don't have a distance which are symmetric.
So usually by mathematical standards, it's considered like absolute in that regard, right?
Yeah.
Okay.
There is like some variant on this definition. Come for example in axiom 1 when you say that x is less or equal to y.
Yeah.
And you have the distance is 0 if and only if x is equal to y. Sometimes this part is omit. This is called pseudometric. And I mean they're used usually because you're talking about function or stuff like that.
So do you learn like which I guess like course or branch of math do you learn this definition that you're giving us? Is this in real analysis or is this in like higher stuff like differential geometry or something?
So usually this is covered in maybe not the first course in analysis, but maybe like when you talk about, for example, when you're dealing with vector space, like analysis on vector space, usually you will introduce metric space first.
Oh, okay. So this is probably like for real analysis for like multivariable.
Yeah, but usually you do it the same. You usually go through this definition and the property of metric space in a more deeper context in the topology course.
Oh, okay. Because I felt I recognized this before, like, because I think I've looked up like certain books about like topology or like I think like differential forms, and I would be like, wait, this seems familiar to me, like this distance thing. And I think it's because I read like a lot of general relativity books for beginners that when you define the metric space, I'm like, oh, maybe that's where I got this from.
Yeah, they're not exactly the same. Like the metric in general relativity is not it's not a metric in the sense of the function I have here.
Yeah,
but
it's a metric tensor. Yeah, it's a metric tensor.
Yeah, but the thing is, so I mean, okay, here maybe I can go on the ramp. So
yeah.
So in differential geometry, if you have a metric, so it basically tells you how to measure a distance at every point.
Okay, you're at one sentence.
At least infinitesimally, if you want.
Uh-huh.
And what you can do is, for example, if you have a curve from A to B.
Yeah.
So maybe let's call this point A and this point B, and this curve gamma. I mean, you have to assume it's smooth and so on.
Right.
What you can do is you can measure the length of gamma.
Okay.
And basically, it will be like something like the length of gamma will be like something like you integrate over gamma over like what do you like you evaluate this thing to like something along those lines. Like you derivative gamma, so you get like the speed, and then you can use the speed to know
why there two gamma primes.
Because okay, so the metric in Riemannian geometry is basically a scalar product.
Oh, okay.
So it takes two elements.
Oh, okay. So like to say like the Pythagorean theorem, for example, it's like it's like x squared plus y squared. The square root of that would be the distance. Something like that. Okay.
Yeah.
This is just extra, guys. This is just basically just extra. This is like I don't think this is like the main stuff that we're learning, but it's something that like if you're really inspired of uniting math and physics together, like this might be something.
So usually this will tell you the length of a curve.
Yeah.
But if you want to know the distance between A and B, you do the crazy thing that mathematician does. Is that let's consider all of them.
Oh yeah. I think we're getting into Lagrangian, right?
And take the minimum. I mean, it would be the infimum, but yeah.
Yeah. I think we're talking about now in physics. I think we're talking about the action now.
Yeah. So there's like a calculus of variation you can use sometime to
there you go, guys. A little bit of metrics. With
which
physics.
one are minimizing the distance, but I mean sometimes there might be exist multiple of them, but. Okay. Now we're done with this term. So
yeah. Just one more thing. Aspire basically said, "This is a really cool way to introduce this subject. It feels like a constructive way instead of a belief system like most math courses I took." There you go, Sasha. Your teaching style is reaching everybody.
Okay, so the reason why I introduced metric space is basically because I'm lazy. Because if I don't do it right now, we're gonna have to introduce the same definition twice when we talk about real numbers.
Well, you're introducing us to some advanced math too, so you know that's like a plus, I think.
Yeah. I mean, I will not go into the deeper theory of metric space. I will just like basically.
We just need it for now.
Yeah, we'll just state the definition like in some useful fact that we can prove easily, and just apply it to the concrete case we're on, so the rational numbers and the real numbers.
So in general, the metric space is just basically just there to define distance for us. That's basically what it is.
Yeah. And it also gives you a notion of topology that we can use.
Okay.
But it also has a little bit more structure than topology. There's like kind of two pieces of data going on. You have like the topology induced by the metric space, but you also have the distance function, which are another piece of data that you cannot always recover from the topology itself.
Okay. All right. So what's next?
Okay. So what's next is we're gonna talk about sequences and convergence. Okay.
So we needed metric spaces to discuss sequences?
Yeah. I mean, I will introduce it as okay. Maybe I will define it. Maybe I will define a convergence of sequence on the metric space, and after that we're gonna specialize in the case of the rational.
Okay.
So maybe let's start with the first thing, which is the obvious thing. What is a sequence?
Right.
So definition: a sequence is a function. So usually we like to call it with a little, with like A, B, or C or something. Mm-hmm. And it goes from the natural numbers and it goes to our metric space.
Oh,
okay, so
that's a
so for now,
I heard that.
So for now you can, I mean, if you're not comfortable with the abstract setting, you take M to be Q, because that will be the case that we're gonna work with it.
Okay, so we can just write for now, for now.
Yeah.
M is Q.
Yeah. I mean, if you don't feel comfortable with it, you can use that. Well, now you can take M equal Q. But it works. I mean, there is no. I mean, other than the fact, maybe it's a little bit more abstract, and maybe it will be hard to focus on. There is no like complication to talk about.
So basically what you're telling us is like M itself, since it's a metric space, and the metric space basically tells us how distances work within that space.
Yeah.
So basically we're just saying, hey, this is M and it's equal to Q because it's basically telling us the distances within Q are going to operate with these rules. That's basically what you're telling us.
Yeah, I mean, technically for define sequence, we don't even need a metric space. We can use any set, but in that case, we will not get.
But you're just doing it to make it easier.
Yeah, we wouldn't get like stuff like convergence and stuff like that. So we better work with the metric space.
You're the teacher, man. Like, go at it. Make it easier for you.
Okay, and so usually a function, we usually evaluate like something like that, right?
Mm-hmm.
But usually people will not write something like that. Usually we'll abbreviate instead of writing as a usual function. Usually what people do is they just write a little lower script like that.
Is that what is that? Is that a Christoffel symbol?
No. This is just a lower indices.
Oh, okay.
So I mean, okay, I'll give you an example.
Oh, is that an arrow? Like you're pointing to the end, like.
Yeah. I'm just saying.
Okay. I thought it was Christoffel symbol. I'm like, wait, what?
Yeah. Okay. Yeah. Maybe I'm a little bit confused. Maybe I'm giving a little bit more confusing information. So let's take M to be Q,
right.
and the sequence will be something like that.
Mm-hmm.
Take AN and you map it to 1 over N. So A is a map that takes a natural number and give you a rational, right?
Right.
But usually people will not write something like that, right?
Mm-hmm.
Usually what people will do instead is they will write N is equal to 1 over N.
Mm-hmm.
So we're gonna stick with this notation, which is probably
Yeah, I've seen that in textbooks a lot.
Yeah, I mean usually people yeah. Usually they don't write it as a function like that, but formally a sequence is a function that go from the natural number and goes to the...
Yeah, because I remember in calculus when you're introduced to sequences, and maybe like in algebra too, they would basically they would show you a sequence, but it's just a list of numbers. but
Yeah.
it's up to you as the student to basically figure out what the function is that the sequence is behaving under.
Yeah. Okay, and now we can give. Okay, I mean we don't want to consider any old sequence. We want some interesting ones. So we're gonna talk about convergence of sequence.
Mm-hmm.
And after that, we're gonna prove some property about that. Convergence of sequence. Okay. So usually I will just write something like that. Let A. Okay, maybe I will just put it as an example. Usually I will write. I will. When I talk about a sequence, I will usually write something like that. Okay.
Okay.
That's my way of writing it. This is a sequence. Let's A and be a sequence on M. So M is a metric space. It's a metric space. Okay.
Mm-hmm.
We say that AN converge to X. We say AN converge to X. If we have the following. Okay. And basically, one of the hard parts of real analysis, this is like really the heart of real analysis right now we're getting into,
Okay.
is understanding this definition. Okay.
Okay.
Like if you understand this definition, you're pretty much set for pretty much the entire rest of the course.
Okay.
So if we have the following, for all epsilon, so epsilon will be, for now it will be a rational number, but usually it would be some real numbers. There exists some rank, let's call it big N, okay? Such that for all the rank that go before after big N, for all N which are greater than N, we have that. Oh, sorry. So I'm talking about the case of metric space.
Mm-hmm.
We have that AN. The distance between AN and the point X, at which our sequence is convergent, is less or equal to our epsilon.
Okay.
Okay, so maybe we can just draw a little picture, and maybe I can try to describe the way I think about it in my head. So I like to think about this guy as some kind of error.
Okay.
I think a lot of people have the same idea. I mean, the same way of thinking of it as me.
Mm-hmm.
And so what you have to imagine, like, so maybe let's just write some. So let's say our M is like some abstract stuff. So maybe something like that. And now we have a point X here, right?
Mm-hmm.
And now we have a sequence. And basically the way you have to think about it is epsilon is some kind of error, and you can pick whatever you want as an error. Like it's some kind of challenge. Like people can challenge you with smaller and smaller epsilon, okay?
Mm-hmm.
So let's say I chose I don't know, epsilon is equal to 1/2, let's say.
Okay.
Okay. So what is this definition is trying to capture is the fact that, okay, maybe I have my sequence here, and maybe like I don't know, so maybe my sequence starts here, A0. And maybe you can do like some random stuff at the beginning, okay? Maybe you can say, oh, I will go there. Oh, never mind, I will go here. You see, you can do some funky stuff, okay?
Mm-hmm.
But at some point, what's gonna happen is we're gonna reach some big N, okay?
Mm-hmm.
At some rank, which are big enough.
Okay.
All the following term will fall into this kind of balls around our point X.
Okay.
Okay.
Mm-hmm.
And they will, and that's the point. All the further term after AN will all be inside of this balls.
Okay.
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 So the thing you have to think is this N here. Maybe some people put a little epsilon under it to remind us that it depends on what challenge we were given, right?
Okay.
On which so the N depends on epsilon.
Mm-hmm.
And basically, you said that an converge to x if for all challenge or for all epsilon greater than 0, you're able to find such a construction. Okay.
So basically, epsilon is just the margin of error, but you can adjust it. Like basically, like if you were turning the dial of a value on, let's say, the volume of a stereo or something.
Yeah. And okay, so first of all, we have to address one issue. So sometimes we call x a limit. Okay?
Right. Yeah, because I think I've heard of this definition before.
Is often called a limit. Okay. And now we have to do a little bit of grammar. We have to, okay, first of all, we have to work out the following. Is it a limit or the limit?
Okay.
So here the difference for people that are not using English, a usually in English just mean like an apple, like it can be like any apple
Singular.
in the bag if you want.
Yeah.
Just mean like there is an apple, right?
Yeah.
The apple is like I mean, I don't know how to put it, but it's like it has some kind of uniqueness, right?
Yeah, like basically it's like the apple of knowledge, like the apple.
Yeah.
It's like basically it has importance, like it's basically apple, the limit.
So, joke aside, what's here the important thing? We want to know, is the limit unique?
Okay.
In other words, is the limit unique? Okay. And what I will show, so now I will give you like kind of a taste of how epsilon proof works. We're gonna show that, okay?
Okay.
So maybe I will write it more formally so that we can not be too sloppy. So proposition. Let an be a converging sequence okay, let's an converge to A and an converge also to B. Then A is equal to B. Okay, so again, maybe I will write it. An is a sequence that takes value in the metric space.
So wait, because I remember you first said that an is to be a converging sequence. Is that basically the same as what you're saying here? Like A is a sequence that takes a value in the metric space, right?
Yeah, so it just means that the element an are inside of big M. So the same setup as before. And then now I have two things. I have that an converge toward A, and I also have that an converge toward B. Okay. So we have two pretender to be the limits.
Okay.
And what we want to show is that A is equal to B, so there is only one. There is only one limit. So let me show you how it works.
Okay.
So here the strategy we're going to use is the following. Let epsilon. So okay, maybe I would write some scratch of the proof to give you what we want to do. Okay, and after that we'll write it formally.
Okay.
So the idea is that we're gonna try to show that the distance between A and B is less or equal to epsilon, where epsilon is epsilon is any positive real numbers. Well, I mean, I guess here we're going to use rational.
Is this
Is
supposed to
any
be say
posi-
where epsilon is
Yeah,
okay.
any positive rational. Okay.
Mm-hmm.
So so what we want is we want this quantity all for every epsilon which is bigger than 0. Okay.
Mm-hmm.
And if we're able to do that, what's gonna happen is that, or maybe here I should have prove something else. Okay, maybe here I'm gonna cheat a little bit. But if we're able to show that the distance between A, B is less than the epsilon for every epsilon, that means that distance of A, B is like very small, right? It's smaller than any other numbers, right?
Mm-hmm.
So what it would mean is that what it will imply is that the distance of A and B is equal to 0. Therefore, A is equal to B because of the axiom we had for a metric space.
Okay, so could you like restate that? So basically, I got to the part where it's like where epsilon is any positive rational number.
Yeah.
And...
So what we're gonna
Mm-hmm.
so what we're gonna do is we're gonna show this inequality all for any epsilon.
Okay.
For any epsilon which is bigger than 0. And what it will implies is that the distance between A and B has to be 0.
Okay.
Okay. And then A is equal to B. Okay. I will take this part to this part as given. Okay.
Okay.
Because we need to prove another property that I forgot to prove, but I will prove it afterward because I just forgot and I want to do this proof before moving on.
Yeah.
But it's not completely obvious that this implication works.
The distance between A and B is 0, hence like an epsilon greater than 0 will lead us to like basically A equaling B. Like that's basically
So what is not obvious is if the distance is as small as you want, it does not necessarily imply that the distance of A and B is 0. I mean, okay, that's true, but it's not obvious. That's called the Archimedean.
That's why I'm restating it. So, like, basically, that's the thing that's not obvious to everybody.
Yeah. The right side
including me.
The right side is just from the definition of a metric space, but going from the left to the right is not obvious. Is the Archimedean property we need to prove.
Okay.
But I will just take that as a granted for now, and we're gonna prove the Archimedean property afterward.
Right.
Okay. So how does it work? So first of all, I will take this epsilon. So let epsilon be any positive rational numbers. Okay. Okay. And now, as an is converging to A, and as an is converging to B, right? So what it means for those sequences to converge, it means that at some point there will exist some. So maybe I can do it for one. Okay, I will do it. Okay, I will take my time for this. So the first one implies that there gonna exist some rank. So maybe let's call it n1. There's gonna exist some positive rank, such that for all the n which are bigger than n1, we have the distance between an and a is less or equal to, and here I'm gonna use a trick. I'm gonna not use epsilon, I'm gonna use epsilon over 2.
Okay.
Okay.
All right.
And first of all, we have to realize why I can do that. Okay.
Okay.
So maybe I will write it on the side just to give you an explanation. So the fact that an converges to a is equivalent to the following statement. For every epsilon, maybe I will put the epsilon prime here just to clarify stuff. There exists some n1 which is greater or equal to 0, such that for all n which are greater than n1, we have the distance between an and a is less or equal to epsilon. Okay.
Okay.
And the point here is that you can choose your. Oh, sorry, I put epsilon prime. I should put. I'm supposed to put epsilon prime here. And the thing is that you can choose whatever you want as your epsilon prime, okay? As long as it's positive.
Okay.
So, and it's supposed to work for every epsilon, right?
Yeah, because you put basically let epsilon be greater than 0. So basically, if it's greater than 0, then basically it should have like a positive half rational number, I guess.
Yeah. So so the fact that I can basically when you have convergence, it means you can pick any epsilon, right?
Right.
And you should be able to find an n1 such that you have this, right? So what I did on the left is I chose my epsilon prime to be equal to my epsilon over 2. That's what I did.
Okay.
I applied this definition in the very specific case where epsilon prime is equal to epsilon over 2.
It's like you didn't have to, but you chose that, basically.
Yeah, and now, so now I justify why I why is that legal to choose epsilon over 2 here? It's because as I said on the right, I can choose epsilon prime to be whatever I want, so I will just use it epsilon 2. And now the question is why we choose a half, and the answer is because you're gonna see. You're gonna see why I use a half, okay?
Okay.
I mean, you have to see it at least once in your life to be able to understand.
Okay.
And for the second, I did it for the first convergence. Now I will do for the second limit point. So I can do exactly the same thing. I will find some rank. Maybe let's call it n2 to not to make
greater
it
than 0, right? Greater than or equal to 0. Okay.
Yeah. Such that for all rank which are higher than n2, we have that the distance between a and b is less or equal to epsilon over 2. So exactly the same reason. And I did so this guy and these guys are exactly the same. I did like the same reasoning. Okay.
Okay.
And now I'm kind of fed up to having I have like 2 rank that I have to go over. So maybe I will just have 1 instead. So I will put n to be equal to the maximum between n1 and n2. Okay.
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 Yep, sounds like it's similar to the absolute value that we just defined.
Yeah.
In some way. Yeah.
Yeah. So now what I'm gonna do is I'm gonna pick some let n be a number which is bigger than n.
Okay.
Therefore, we can use our bounds, right? Therefore, we have the distance between an and a is less or equal to epsilon over 2, and the distance between an and b is less than epsilon over 2. Okay?
Okay.
But now I have to remember what's my initial goal. My initial goal is to show that the distance between a and b is less or equal to epsilon. Okay, now I will write distance between a and b, and as somehow I need to use those bounds that I have here to figure out that the distance between a and b is less or equal to epsilon. Okay.
Okay. So our goal is to prove the distance of a and b is equal to epsilon, right?
Is less or equal to epsilon.
Less than or equal to. Okay. I just want to rewrite our goal so that way we remember.
Write it right there. Yeah, I will write it on the bottom. Distance between a and b is less or equal to epsilon. That's our goal.
Yeah.
Okay. And there is one trick. There's one trick we can use. So we have kind of 2 inequality, and I mean basically we're almost there, right?
Yeah.
One of them has a and the other one has b, right? And they have like the same factor a/n. So we would like a way to stitch those inequality together to get the thing we want.
Okay.
Do you have a slight idea on what we could use?
So basically, we're just trying to like make the distance from an to a and an to b. Basically, we're just trying to make that, I guess kind of trick it to basically give us like distance of a b.
Yeah.
So
I mean,
uh-huh.
we might not be able to know exactly what's the difference between A and B, but at least we will have some bounds.
So basically, you can add, like, when I was thinking about it, just adding the two epsilons together, because
Yeah. Okay. You pretty much have the you pretty the
because then you would get like two two epsilon over 2, and then basically you would like basically just like get rid of the 2's, and then you're automatically get epsilon at that point.
yeah. But now I just have to justify why, right?
Yeah.
And maybe I will just rewrite a little bit my distance function, so the thing I wrote here a little bit.
And I think you did the half of epsilon. This is my guess, but like not only is it for that trick, but also it seems like A is sort of like 1/2 of that distance, while B is the other half. Like that's how I see it in kind of like, I guess, distance wise.
So I rewrote the distance. I just swapped the argument inside of the distance function, so it does not change anything because the distance function is symmetric.
Yeah.
And now I'm gonna use the triangle inequality. Triangle inequality in real analysis is always your best friend.
Okay.
So what we're gonna use is we're gonna write the distance between A and B. So if we use the triangle inequality, the distance between A and B is less or equal to the distance between A and A of n, plus the distance between A of n and B. Okay. But those two guys on the right, we control them. We know what they are.
Yeah.
I mean, at least we have a bound. We know they are less or equal to epsilon over 2. So what we are left with is that we get that this guy is less or equal to epsilon over 2, and this guy is less or equal to epsilon over 2. So basically, you kind of predict what's gonna happen. So I have epsilon over 2 plus epsilon over 2. So this is just epsilon. Oh gosh. Wait. Do you still see the board?
I still see some of it, yeah. Because like I just rewrote the epsilon over 2 part.
Yeah, I just saw a line. I just have a line right now.
Oh, okay.
Oh god damn it.
Don't worry, guys. This happens to us all the time.
Okay, maybe I can still write and you will still be able. But I don't see what is above me, so maybe I will write on stuff. Okay. So basically, did I write epsilon on the right?
No, I don't see your epsilon. I don't see your epsilon after the equal sign, right?
Okay, so is that on the epsilon? is that somewhat after the?
Yeah, I don't see what else you're writing now. Oh, now I see your epsilon. Now I see the epsilon you wrote.
I don't see the equal sign, so I don't know if it's in a good place, but whatever.
Yeah, it's after the equal sign. You're good.
Okay. And so I will guess that the inequality is somewhere there. Is that the case?
No, you just basically wrote a dashed line like after goal, like under goal. So
Okay. So I mean, the important part is that we now show that the distance between A and B is less or equal to epsilon.
Yeah, I can see that what you're writing down.
And epsilon was chosen arbitrarily.
So I guess with this proof, we can say it's the limit, right?
Yeah. Arbitrary, therefore. Distance between A and B is equal to 0. Thus, A is equal to B. Okay. Here I've cheated. Here I've used something implicitly. I used the Archimedean property.
Archimedean property?
Yeah.
What's that?
So we're gonna go over that, okay? So maybe we can just start over with the new whiteboard because this one is kind of broken for me.
Okay. Yeah, we can do that.
Wait. Actually, if I just write under it, I think it's fine. As long as you're able to see what I'm writing, I think I will be fine. Because now it's fine on the new part I wrote, but I don't see the old part.
Okay.
So I guess it's still fine. Okay.
All right.
And I will just make sure that I just don't write nonsense. So the Archimedean property is the following. I'm not sure how the spelling works for that thing. Archimedean. Okay, maybe I will look on Wikipedia for the spelling because I have doubt on that. Archimedean property. Archimedean? Well, it's a strange spelling. The Archi...
And this is when we're actually getting into real analysis now, right?
Yeah. Okay, the Archimedean properties. Okay, it said the following.
Okay.
Hold up, I will just make sure I don't mess it up.
Mm-hmm.
Yeah, basically it said the following.
Mm-hmm.
If y is a positive rational number, okay.
Okay.
Well, actually, we're gonna use x and y, which are positive. Okay.
Okay.
Then there exists n, a natural number, such that n of x is bigger or equal to y.
Okay.
Okay, this is called the Archimedean properties.
Okay, so there exists an n, a small n, which is an element of big N, natural numbers, and n times x is greater than y, right?
Yeah.
Okay.
I mean, it's pretty easy to prove. So what you can do is, okay, first of all, you can assume that x is, first of all, we're gonna write x as y as fraction.
Okay.
And we can assume that they have the same denominator, right?
Okay.
Assume x is equal to a over b and y is equal to c over b. Okay. If they don't have the same denominator, you can just multiply the two denominator together, and you. I mean, it's pretty standard stuff. Okay, if x is well, I guess here I'm gonna use implicitly the Archimedean property over z, so I guess it will not be a complete proof, but I mean, yeah, it will depend on stuff on the integers, but so x is and x is bigger than y if and only if na is bigger or equal to c, right? Because they have the same denominator in that case.
Okay.
Okay. And I mean, it basically follows from that, because what you can do is, for example, is you can take if x and y are positive, it means that a and c are positive, right? And clearly, for example, if you take n equal to c, you have that CA is bigger or equal to C, right? Well, I guess we have to take C plus 1 because we're going to have A equal to 1, which we're going to give you a counter example. So we're going to take n equal to C plus 1.
So n is equal to C plus 1?
Yeah.
So then
we're going to end up...
C plus 1 multiplied by A is greater than C.
Yeah. And so this guy will be basically your n, and this showed the Archimedean properties.
Okay.
Okay, I didn't very prepare, so it's a little bit sloppy, but this basically showed the Archimedean properties.
So the Archimedean property is just mainly stating that, let's see, basically a positive rational number, like basically, I guess like in succession to another. Is that what it basically covers?
So if you have a positive, so if you have two positive rational numbers,
Uh-huh.
I mean the second one doesn't have to be positive, but the first one has to be. You
Okay.
can always multiply by some natural number in such a way that this thing will be bigger than the other.
Oh, okay.
So basically, this thing is to basically. So there is a branch of analysis which is not very used nowadays, but it's called non-standard analysis.
Uh-huh.
And in non-standard analysis, you have a notion of infinitesimal,
Okay.
which are like a number which are smaller than all the other. Okay.
Okay.
And those numbers will have the Archimedean property because they will be, for example, you might have an, I don't know, maybe we can call it an infinitesimal epsilon.
Yeah.
If you multiply epsilon by like some natural number, it will not always never be bigger than 1.
Mm-hmm.
And basically, the Archimedean properties said that this cannot happen inside of Q and inside of R.
So is the Archimedean property just mainly used for like the numbers in between, let's say for an abstract example, or maybe a more solidified example, like between half and 1. So it's involved with like the numbers that we cannot possibly count in between there.
Well, no. Well, I mean, if we take literally what the Archimedean properties say, example for 1 and 1/2 and 1, it would just say that for you can find some natural numbers such that when you multiply it with 1/2, you get something which is bigger than 1.
Uh-huh.
And basically, that's what that's all the Archimedean property tell you.
Oh, okay.
And maybe I can teach. Maybe I can tell you why. Maybe I can write one of the consequence of the Archimedean property is the following. Okay, if f is a number, is a positive number, let's say.
What was the first word you wrote?
Consequence.
Oh, consequence. Okay.
If x is some positive rational.
Uh-huh.
Or equal to 0, and for all epsilon greater or equal to 0,
Mm-hmm.
we have that x is less or equal to epsilon, then x has to be equal to 0.
Okay.
This is pretty much the property I used before, right?
Uh-huh.
The proof.
Uh-huh.
So I used the fact that the distance between A and B was smaller than any epsilon
Mm-hmm.
to conclude the fact that distance of A and B is equal to 0.
Okay.
So why it doesn't imply that is because of the following. Suppose that this is not true, okay?
Okay.
So it's going to be a proof by contradiction. Suppose this is not the case. Therefore, x is not equal to 0, okay? So what's gonna happen is let's fix like some epsilon maybe. Okay, let's take some very specific value of epsilon. I mean, just for simplicity, let's take epsilon equal to 1, okay?
Okay.
So using the Archimedean properties,
Mm-hmm.
Archimedean properties. Don't really throw me that it's spelled with the E instead of an I, but I guess it's English way of writing Archimedean. Okay. The Archimedean property tell you that there exists some natural number n.
Okay.
Such that n times x is bigger than epsilon, right?
Mm-hmm.
But if we just divide by n, because n is n we can assume it to be positive, because if it's equal to 0, it's obviously false, because otherwise we're gonna get 0 on the left side and the right side is strictly positive.
Uh-huh.
So if we divide by And what we are left with is that x is bigger or equal to epsilon over n, right?
Mm-hmm. Yep.
And this show you this is a contradiction. This contradicts the fact that x is smaller or equal to epsilon over n. Because at the end of the day, epsilon over n is still a positive number, right?
Yeah.
Therefore, the property we wrote at the bottom that x should be smaller than any positive quantity cannot be true, right?
Yeah.
Because we just found a counterexample. We found that epsilon over n violate this principle.
Because it's basically saying that x is less than or equal to epsilon divided by n.
Yeah. So our hypothesis said that x should be lower or equal to epsilon over n, but we just proved that we have that x is bigger than or equal to epsilon over n.
Yeah, because x is supposed to be either equal or greater than 0, and for all epsilon greater than 0, it basically is like x is supposed to be less than or equal to epsilon. Then x is 0 in that case.
Yeah, and basically if we look at our proof, what we did is we supposed that x was not equal to 0, right?
Right.
And this led to the contradiction, therefore x has to be equal to 0, which ends the proof.
Yeah, because we chose epsilon to be 1, right, in this example?
Yeah.
So then it'll be 1 over n. So therefore...
We could have read something like that, yeah.
Mm-hmm. So then, yeah, so x has to be greater than or equal to 0. And then x is supposed to be greater than 1 over epsilon over n, which is 1 over n. Okay.
So basically, this thing we could say there is no infinitesimal inside of the rational number. There is no like number which are like infinitesimal. Like even though if you multiply them by a natural number, you still don't get something which is bigger than 1 or something.
Wait, say that again?
So one way to think about this property is there is no infinitesimal inside of the rational numbers.
There is no infinite what?
Infinitesimal.
Infinitesimal. Oh, okay.
Inside of the rational number.
Oh, inside the rational numbers. Oh, so basically, like, I guess with the real numbers, like, what we grew up with is basically knowing that, like, you know, after a half, it's not basically just 1. Basically, a half, there's, like, a lot of, like, almost an infinite amount of numbers contained in between 1 and a half, right?
Yeah.
But this is basically saying that, oh, in the rational numbers, we don't have that. Like,
it's not what it's saying. It's saying, like, okay, so you see when people do calculus, okay, let's go back to Newton and Leibniz.
Okay.
So Newton and Leibniz were thinking like something like along those lines. For example, if they want to define derivative, what they do is they say, okay, the derivative of a function at I don't know x0 is f of x plus some epsilon minus f of x. Forgot the 0 over epsilon. Okay.
Okay.
Where epsilon is I'm not sure if I can spell that. Infinitesimal. Do you want to spell it?
Yeah, I'll try to spell it. So infinitesimal. I think somewhere around there.
Yeah, and the thing is, those are supposed to be like special numbers. At least in their mind, they were supposed to be special number. For example, if you multiply an infinitesimal by like some positive quantity,
yeah,
like n is a natural number. let's assume n is not 0, then you should still get an infinitesimal.
Okay.
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 And this quantity is like very small. Okay.
Okay.
But I mean, yeah, it's not very a formal mathematical thing, but at least in the time of Newton and Leibniz, they were thinking in terms of those guys.
Okay. So.
And what we.
Okay, go on.
And what we've basically showed here in the Archimedean properties is we showed that there is no infinitesimal inside of Q. There is no epsilon like that verify this property.
So.
Because you can. Because, for example, you can always find a n such that n times epsilon will be bigger than 1 or whatever number you want it to be bigger of. So there is no such thing inside of the rational, and also there will be no such thing inside of the real numbers. But I'm getting a bit ahead of my time, ahead of myself.
Okay, so basically they're infinitesimals, right?
Yeah.
And basically the Archimedean principle basically shows that whenever you're dealing with, let's say, a rational number, right? Let's say that's like x, right? And then we multiply it by n, whatever n may be, like the natural numbers, right?
Yeah.
It will always be over 1, right?
Yeah.
Thus
over
being, being more than epsilon, correct?
Yeah.
Okay. So basically, it's always going to be like a number greater than epsilon. So I think what I'm getting lost at is it basically saying that within the rational numbers we cannot access the infinitesimals? Is that what it's saying?
Yeah, there is no infinitesimal inside of the rational.
So, does that lead us into, I guess, what is it, the axiom of completeness?
No.
Oh.
The real number also will not have the infinitesimal inside of them.
Oh, okay. So, basically, the Archimedes principle is basically saying we won't have infinitesimals in the rational numbers, right? Is that what it's saying? Okay.
Yeah.
Okay.
So they will not have a quantity like that. So the thing that Leibniz and Newton were thinking are not number in the definition of the rational number and the real number we're gonna give.
So the Archimedean property just proves that we won't have infinitesimals, at least right now in the lesson, is basically not in the rational numbers and lower from that, right?
Yeah.
Okay.
And I mean, it will be useful because okay, so this is more philosophical what I told you, but usually in practice we will care about this thing I just put a green rectangle over it.
Okay.
That if a positive quantity or equal to 0 is less or equal to epsilon for any epsilon, then it has to be equal to 0. That's going to be the thing we're going to use a lot of time.
Oh, okay. I see.
Okay.
All right.
That's more like the practical stuff of the Archimedean properties.
Okay. And so I guess we've reached our time, but what are we looking forward to for next week, Sascha?
So for next week, so now we talk about sequences and we basically what it means to converge. So I'm probably gonna give you a lot of exercise. I mean, okay, for this week I think I will still give you exercise on the construction of the rational number.
Okay.
And for the next week exercise, you're gonna play a lot with sequences and converging and proving stuff about limit and stuff like that.
Okay.
And we're gonna introduce a Cauchy sequence.
Okay.
So there's gonna be one of the day, and the other day maybe we're gonna talk a bit about rings again.
Oh, okay. We're gonna go back to rings. So it's gonna be the Cauchy sequence, a little bit more about rings, and Go on.
So maybe I can give you a little bit of a guidance. So what's gonna happen? So basically we're gonna have sequence of rational.
Okay.
I mean, we pretty much went through that today, but we're gonna go. There's a lot of stuff to talk about that, so we're gonna do that again the next time.
Okay.
And it makes sense for sequence of rational to add them.
Okay.
It even makes sense to multiply them.
Yeah.
So what we will get instead is that the sequence of rational numbers is actually a ring.
Uh-huh.
And inside that ring, you have a subring, which is like basically a subset which still have like a property of the ring, which is called which are the Cauchy sequence. Okay.
Okay.
And so, I mean, one important fact is that the set of Cauchy sequence form a ring. So it's going to be an important fact. Okay, I can write it. Cauchy sequence.
And the Cauchy sequence is basically the ring and sub-ring within the rationals. Is that what you're saying?
So Cauchy sequence form a ring. So they are inside of the ring of sequence, of rational sequence.
Oh, okay.
Okay, so I mean the word ring is just a fancy way to say that we can add them and multiply them together.
Does this also
Okay.
relate to a Hilbert space in some ways with Cauchy
yeah, so-
sequence?
Yeah, Hilbert space are related to Cauchy sequence. So yeah, I guess when we had built the real number, you will have your first example of a Hilbert space.
Yeah, because I heard that you need like Cauchy sequences within a Hilbert, like to actually define a Hilbert space. And what the
Yeah,
Cauchy
so-
sequences does is that since Hilbert space is a vector space, if you go, I guess like all the way, like if you imagine a vector space is like a big circle, you can't go towards the edge of the vector space because it will give you a number and not a vector. So what the Cauchy sequence does, I think this is what I've heard, is that it will allow you to count that number at the edge of the vector space within the vector space.
Yeah, so basically the upshot of Cauchy sequence. So we have convergence sequence and we have Cauchy sequence. Okay.
Yeah.
And if our space is well behaved, it means have an axiom of completion. The two should be exactly the same thing.
Like what two should be the same?
The Cauchy sequence and the convergence sequence should be the same thing.
Oh, okay.
If we have axiom of completion. If we don't, then we're gonna have some missing point, and they're gonna have Cauchy sequence which are not converging, because we'll be missing the limit points.
So like the axiom of completeness allows us to confirm that the Cauchy sequence will be would you say equivalent to
Convergence sequence.
convergence sequence? Okay.
Basically, Cauchy sequence is just like a clever way to write that a sequence is converging, but without talking about converging to what,
Yeah.
without mentioning the limit points. And
or like the elements within the space, right?
yeah, that's kind of the clever thing about Cauchy sequence.
Yeah.
And so basically what's going to happen is that Cauchy sequence doesn't converge, see the other point that we are missing inside of the rational.
Oh, okay.
And I will give you like, I will do a little project. I was thinking about giving it to you, but I kind of write the thing yesterday, but
Yeah.
it might be a little bit too hard for someone who's just getting started to analysis, so maybe I will...
I can put it to the side, and like once I gain more, like I'll probably ask you, "Am I ready to do this now?" And you could probably tell me yes or no.
But I still want to do it because it's kind of a satisfying thing to do.
Yeah.
We're gonna show that square root of 2 is not a rational number. That's something that you might have seen.
Yes, I've seen that many times.
But we're also gonna prove that we can approximate square root of 2 by a sequence of rational numbers.
Oh, okay. Yeah, that I have not done.
And what's gonna happen is this sequence. So this sequence, I mean, at least morally, it's gonna be convergent to square root of 2, right?
Uh-huh.
But the thing is, as we're working over the rational, it will not converge because square root of 2 is not a part of the rational number.
Okay.
So what we're gonna end up is we're gonna end up with a sequence which is Cauchy, but it does not converge, because the point on which it's supposed to converge is not part of the rational number. So we're gonna get into trouble with that.
I'm guessing the way that it sounds, it seems like that would be done by proof of contradiction, if you were doing the proof of this, or am I just assuming too much?
So basically, we're gonna first have to show that we're able to find like such a sequence.
Uh-huh.
And I mean, yeah, last time I asked you if you knew some programming, because what is gonna be fun with this exercise is we will be able to write a program that compute the square root of 2 with arbitrary precision. But I mean, I will show you the way we do it on the mat, and I will prepare a little Python script so I can show you that if we give our a little algorithm that we cook, it would actually compute square root of 2 with arbitrary precision.
Oh, okay.
so it's gonna be a little bit of fun.
Yeah, it sounds fun.
Yeah. So it's gonna be a very, I think it's gonna be a very cool example, because you're gonna see like what it's mean for a Cauchy sequence to be what's an example of a Cauchy sequence which does not converge, and kind of see why this sequence does not converge. So it's gonna be fun.
Okay, yeah, that sounds like exciting stuff. So I guess you guys know what you're gonna look forward to in the next couple of streams.
Yeah.
So Sasha, do you have anything to say to our global audience before we depart for today?
So don't forget to follow Matt Spellbook and on YouTube and Twitch, and drop a likes on YouTube. And what do you drive on Twitch? I guess the bell.
Yeah, basically drop a follow on Twitch if you like math, physics, or just want a productive stream to basically get yourselves doing the stuff that you need to be productive with on the computer or maybe your tablet or something. But yeah, thank you, Sasha. I will catch you next week for our next lesson.
All right, see ya.
All right,
Have a nice lesson.
Same to you. Have a good weekend.
See ya.
Okay, guys. First of all, thank you for all those that dropped a follow. Also, I want to give a quick shout out to Zach, because I saw that he gave me a shout out like probably before we started stream, so I'll give him a shout out. If you're not familiar with Zach's content, aka e to the 2i pi, he's basically I think he is a professional mathematician, because like I think he's getting his PhD soon. So if you have any math questions, you can basically go to him and he'll probably like have the answers for you, especially with infinite series. He's really good with infinite series. He loves talking about that, especially linear algebra stuff. So be sure to check out his content. And like Sasha said, I have a YouTube channel. I will put that in the chat for you guys on Twitch. And if you would like to join our Discord server, you're more than happy to join our Discord server if you basically want to talk more about the stuff that me and Sasha discussed, and maybe you guys can probably educate me on stuff that maybe he missed, or maybe like you have questions for like Sasha about, you know, what we went over. I'm pretty sure that he'll be willing to help on the Discord server if you want to actually ask him some questions. In addition, I also have my Uncle Talks channel where I play video games. Sasha sometimes drops in there sometimes, so like maybe like if you guys are still into like continuing on with the math discussions, you can continue on in the chat in my video game channel. Especially when Sasha is like the only one in my chat and like we're just talking about nothing but math while I play video games. Sometimes that happens. But yeah, you can also check out my Uncle Talks channel where I play video games. But yeah, and if you're watching this on YouTube, first of all, thank you for watching the video. In addition, all the links will be in the description down below, and I'll be sure to catch you guys next time. So thank you guys for joining us today, and always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you guys next week for the continuation of our journey into the numbers. So take care, guys. Bye-bye.